Welcome to today's Explainer. Today we're looking into a mystery that honestly completely surprised me. We're going to explore exactly why one of the toughest, most resilient materials on Earth can just suddenly, out of nowhere, catastrophically fail when we least expect it. We rely on stainless steel for literally everything, from our kitchen sinks to massive ocean liners, and we generally just assume it's practically invincible. But, as we're about to see, it has a very hidden Achilles heel.
So let's dive right into this incredibly intriguing puzzle. Have you ever noticed that a piece of metal that effortlessly survives the harsh, salty environment of the open ocean can somehow be completely defeated by a tiny, almost invisible gap? It's crazy. You could have a perfectly pristine stainless steel plate, but right underneath a totally standard bolted joint, this violent corrosive attack is happening. Why does being stainless suddenly just stop working? Simply because two pieces of metal are touching? Well, to figure this out, we need to break down the chemistry of rust.
Which brings us to Section 1, the ingredients for rust.
Right, so before we investigate our microscopic crime scene under that bolt, we first need to identify the exact chemical suspects required to break down metal. It's really not as simple as just getting a piece of metal wet. The first essential ingredient in this whole process is moisture. But actually, it's not just any moisture. Corrosion usually kicks in when the surrounding humidity hits a very specific threshold of 60%. If the humidity is below this, say around 30 or 40%, the metal generally stays totally safe. But the second you hit that 60% mark, the environment becomes just damp enough for the corrosion process to wake up.
In engineering, this specific threshold is known as critical humidity. It's formally defined as that 60% moisture level where metal corrosion actively begins. But here is the major plot twist. While you'd probably think the water itself is the main attacker eating away at the metal, it's actually not. The water is really just the accomplice. It simply creates the environment, the liquid pathway, so to speak, that facilitates the real crime.
The true culprit lurking inside that moisture? Dissolved oxygen. Water, H2O, doesn't actually cause the rust directly by itself. It's the invisible oxygen gas dissolved within that water that's the primary driver of the whole rusting process. It's this dissolved oxygen that acts as the aggressive agent, reacting chemically with the metal to break it down. Think of it like this. Water is just the getaway vehicle, but dissolved oxygen? That's the driver.
Let's move along to Section 2, the oxygen danger zone.
Now, this is where the story gets really wild, especially when we start comparing different types of metals and how they react to this dissolved oxygen. It's a fascinating comparison. Normal carbon steel behaves exactly how you'd expect, right? As oxygen levels in the water increase, the steel just rusts faster and faster. It's a direct proportional relationship. But stainless steel, it plays by a completely different set of rules. Stainless steel has this brilliant chromium oxide shield on its surface. And ironically, it actually requires a certain minimum amount of oxygen to survive. It absolutely needs that dissolved oxygen to constantly rebuild and regenerate its protective shield. If you starve stainless steel of oxygen, it ironically becomes incredibly vulnerable.
Just to give you a baseline for how much oxygen we're actually talking about here, normal tap water or even ocean water contains about 8 parts per million or ppm of dissolved oxygen. As long as the stainless steel is exposed to the standard 8 ppm environment, it has plenty of oxygen to maintain its chromium shield. Out in the open ocean, despite all that corrosive salt, it stays completely pristine because it's essentially breathing in that 8 ppm of oxygen to keep its armor strong.
So these three thresholds basically act like a Goldilocks zone for steel. 8 ppm is normal water, it's completely safe. 4 ppm is the absolute minimum amount of oxygen needed for the metal to maintain and rebuild its protective film. But then we hit 1 to 3 ppm. This right here is the absolute danger zone. In this highly specific range, there is suddenly not enough oxygen to rebuild the chromium shield, but, and here's the kicker, there's still just enough oxygen to actively cause rust. It is literally the worst possible environment for stainless steel to be in.
Which brings us right to Section 3, the Achilles heel, crevices.
So how on earth does stainless steel ever end up in an environment with only 1 to 3 parts per million of oxygen if normal water has 8? Well, the answer lies in a hidden world that our naked eye can't even see. The microscopic geometry of how we build things. Basically, any tiny gap creates a completely isolated micro-environment. Think about a tightly fastened bolted joint, a nut and washer pressed together, overlapping metal plates, or even a barnacle clinging to a ship's hull. To us, these look completely flush, but at a microscopic level, there is a tiny, tiny gap between them. And that microscopic gap is exactly where the magic of the danger zone happens.
So the crucial point here is this 4-step chain reaction. Step 1. Water seeps into that microscopic gap. And remember, you only need 60% humidity for this to start. Step 2. Because the space is so incredibly tiny, no fresh water can easily flow in. The oxygen gets used up, and the level plummets straight down into that 1 to 3 ppm danger zone. Step 3. Starved of oxygen, the protective chromium oxide shield absolutely shatters. And finally, Step 4. With the armor gone but a tiny bit of oxygen still hanging around, a vicious concentrated attack called Crevice corrosion takes over, and it just eats away at the metal from the inside out.
Now you might be thinking, well, let's just stop building things with gaps. But as any structural engineer will tell you, it's virtually impossible to build without bolts, nuts, and overlapping joints. We can't just wish crevices away, right? We can't weld every single piece of machinery in the world into one giant solid block. Because we literally have to use these joints, we desperately need a scientific rescue to save our stainless steel from this inevitable crevice corrosion.
Enter Section 4, Molybdenum, the ultimate fix. So when structural engineering reaches its limits, chemical engineering steps in to save the day. Engineers had to find an alloying element that could be added to the steel to protect it when those oxygen levels inevitably drop. Let me introduce you to molybdenum, known on the periodic table as Mo. Molybdenum is basically the ultimate oxygen bodyguard. It has a phenomenally high affinity for oxygen, meaning it is extremely attracted to it and bonds with it intensely. By adding this specific element into the stainless steel mixture, metallurgists created a brilliant defense mechanism designed specifically for those starved microscopic gaps.
But how much do you actually need? Well, by alloying the metal with a minimum of just 4% molybdenum, engineers discovered the magic formula. If you drop in at least 4% of this incredible element, you stop crevice corrosion dead in its tracks. It's a highly precise recipe that completely changes the durability of the metal in those dangerous microenvironments.
And here is exactly how it works on a chemical level. In that tiny, suffocating gap where the oxygen drops to 1 to 3 ppm, the chromium shield would normally just dissolve. But when you have 4% molybdenum in the mix, it stubbornly holds on to whatever microscopic bits of oxygen are still left. It essentially anchors the oxygen in place. Because molybdenum just refuses to let go, it completely prevents the chromium oxide shield from breaking apart, keeping the metal entirely safe, even when it's stuck right in the dreaded danger zone.
It's honestly amazing when you really think about it. Just 4% of a specific element stops a microscopic chain reaction that could otherwise bring down an entire structure. It really makes you wonder about the brilliant, invisible engineering surrounding us every single day. If our bridges, ships, and buildings are constantly fighting off this invisible threat hiding inside microscopic crevices, what other unseen chemical battles are our metal alloys fighting right now just to keep our built environment from collapsing right beneath our feet? Keep that question in mind the next time you look at a simple steel bridge or a bolted machine. Thanks for joining me on this explainer, and keep exploring the amazing world hiding in plain sight.